Hi. Is there a lecture slides PDF for this week?
No, no, we're gonna be writing this all down together. All right, welcome everyone. This is going to be the start of our module number 3, which is the first dip into digital communications. So we're going to take a kind of a broad view of what it means to communicate digital information and what the pieces of the puzzle are going to be, kind of from a systems perspective. And then by the end, we will be able to talk meaningfully about what are the different kinds of digital modulation schemes and why and when would you use each of them. Now there's a pretty broad goal for this unit, but at least we'll have the introduction about how one could even talk about why QAM is better than or worse than pulse amplitude modulation. Okay. And in answer to the question, the slides are not ready for public consumption yet, so we are all going to be working off the whiteboard today. Before I launch into that, are there any questions from the crowd on homework or logistics or anything like that? Okay, so this is our module number 3, Intro to Digital Modulation. Okay, so the picture that I have in my head when I talk about a digital communication system, it looks something like this. So there is a source of information, and that source, before it gets transmitted, you can think about it being encoded in actually 2 sequential ways. So the unoriginally named source encoder, and what comes out of the source encoder then can get passed into what is reasonably called the channel encoder. And this is then what is transmitted. So this is what's transmitted. Be that over radio waves, like RF through the air, or via twisted pair kind of wireline communication is the term. So I'm not trying to be specific about whether we're doing wireless or wired. This block diagram applies to both. And so regardless of how you are going to be sending that from one place to the other, it's the information, or the signal, I should say, will have to pass through the channel. So this is something that was not really stressed in my undergraduate, is that a communications channel is just a system, right? It takes an input, that is the thing coming from your transmitter, and it maps it to an output, the thing coming to your receiver. So if you think about channels as systems, I think it starts to make this whole thing a little bit less mysterious. So then on the receive side, you can actually do the exact inverse of both of these operations. So we call that channel decoding. And then source decoding. Okay, so the reason that it's helpful to think about it in terms of source coding and channel coding is the fact that between these two, in digital systems, these signals are both binary. This is a binary interface. Which all that means is that this is zeros and ones, and this will similarly be zeros and ones, traveling from right to left. Now that seems kind of obvious. Okay, it's a digital communication system. We're sending zeros and ones, but think about the other signals in this block diagram. This, physically, when you think about it, is a continuous time waveform. Right? At its heart, every single channel is going to take a continuous time voltage and change it into another continuous time voltage. We might model that channel as operating in discrete time, but the physical reality is that it's a continuous time world, and we're just living in it. So same over here. This is continuous. And then whether the source of the destination is continuous or discrete, that is kind of unclear. But the important part is that in the middle is going to be binary, which means that if we can design a channel encoder and decoder to handle bit strings coming in, we don't care where those bit strings came from, right? We can separate the design of these two sections, right? We can design a channel coder saying, okay, our channel code will take in bits and spit out waveforms. Our decoder has to take corrupted waveforms and spit out bits. Those bits should match up, but it's not our job to represent what those bits actually represent. Conversely, a source coder doesn't care about RF, right? A source coder takes, unless the thing it's encoding is RF. But if this is, say, I don't know, the audio coming into my microphone, then the source coder is the system that takes that audio, continuous time in this case, and maps it to bits. Now the microphone in this headset has no idea about antennas or attenuation or anything like that. It's just responsible for taking the pressure waveform coming out of my mouth and translating it into bits. Okay, so this is the power behind kind of the source and channel decomposition, thinking about it in two separate blocks. And I think we're going to adopt that policy because it makes talking about each of the separate ones easier. In the one, I just have to make sure that I put bits in the right order. And in the other, I just have to make sure that I take bits and I map them to waveforms. Questions on this decomposition, or like an instance where you think it might not be applicable?
Question. So source encoding doesn't care about time at all.
I don't think that's true. I think that if I am building a source encoder, I will want to know the rate at which signals are coming in, and the rate at which you're expecting bits to come out. So I think a feature of a source encoder would be, I need 1 megabit per second output, or 10 megabit, or gigabit, or whatever. So I think that the source encoder has to be concerned with time, because the rate at which bits come out will be relevant.
Cool.
And the reason that that's important is because one of the primary jobs of a source encoder and decoder is what we call error detection and correction. So one of the major features of a source encoder is error detection. Now we're going to get into this in some gory detail in a couple weeks, but the idea is the data that I need to encode is going to be whatever I choose to encode it as. It's going to end up with a series of bits. I could choose to just send those bits and then basically cross my fingers and hope that none of them get flipped. Because if any of them get flipped, then what is going to come out on your end of the audio is going to sound different than what I'm saying. An alternative approach would be, let's take the bits that represent what I'm saying and then inject some extra bits into there. We call those error correction or error detection bits. And so what you end up doing is you send up more bits than you would need to just represent the bare bones data. But the advantage of sending extra bits is if you choose those extra bits wisely, those extra bits can actually tell the source decoder how to correct for errors. Okay. So broadly, what I just described is called forward error correction, that we do something ahead of time to anticipate errors in the bits that get received, and we can then undo those errors up to a point. And lots more on that in probably the last 2 or 3 weeks of the quarter. But what we're going to do first is we're going to focus on the channel coding. And you've actually already seen an example of a partial channel encoder, and that was this bit stream being mapped to a, what was it, a return to zero bipolar mapping. So that's that operation. So taking bits and mapping them to voltage waveforms, that is broadly what a channel encoder does. And then decoder would be the reverse. Okay. So I'm looking at the notes I jotted down here that I want to talk about, and part of what we should talk about in a digital communications course is why go digital anyway? Why don't we just continue trying to send analog waveforms? If you did that, then you could skip the entirety of source encoding, because that's what 314 did, right? You have a message signal, M of t, and we need to send that. So do something to it, make the FM signal out of it, and then decode it. So in 314, you jump straight from source to channel coding. And this is why I hesitate to even talk about this, because that seems like such a silly question to ask in what is rightfully called the digital age. You're asking, why should we communicate things digitally? Well, there are two fundamental answers to that. One, the data tends to be digital in the first place. Okay, so the microphone here that I'm using is digitizing data. If I then had to map those back to sound waves and then send that, that would be an extra step. So if I've got digital data, I might as well focus on communicating it digitally rather than in an analog fashion. But the other is perhaps less obvious, and that is, if you have to send data over multiple hops, in an analog system, the noise is going to accumulate with each distance of a hop. Okay, so to go way old school, the old telegraph network, if you were sending a signal across, I don't know, the state, then it would go through intermediate telegraph offices, and the signal that the telegraph office would receive would be noisy, and the signal that they would send would similarly be noisy. But if you think about a router, and sorry, fast forward to today, if I'm sending data from this computer to your computer, every time that data goes through a router, it gets checked for these bit errors that I was talking about. And so what you get is a more robust to noise system, because you don't end up getting accumulation of noise over distance. Because at every intermediate hop, the signal is made clean again, and then sent, and then noisified, and then cleaned up, and then sent again. Now, each of those cleanings can introduce errors, but that's why we have error correction. But at the end of the day, sending this signal around the world, it's no noisier than if I send it to the next room. And that is something that you get in digital that you don't get in analog communication systems. Okay, so if you want, so I'm going to focus a little bit more on source encoding because the rest of the lecture is going to be on channel encoding. So let's take our source encoder and blow it up. So generally, if this is a continuous time waveform, then the first thing you need to do is sample it. You take those samples, and probably the next thing you're going to need to do is quantize them. Right? We have only a finite number of bits that we want to assign to every piece of data. And so to choose which bits we assign to which piece of data, we have to round. And so this is the action of quantizing. And then what I was talking about with for error correction, that would come in this last box, which is just generally called the discrete encoder. So if this was something like x of t, then this sampled signal would be x of n, which would live, say, as some real number. And then the quantizer would represent this with, say, q of n, but that would live in some discrete world. And then the discrete encoder would take those probably bits. So if this happened to be 5, and this would then be, or sorry, 5 point, whatever, some continuous time function at a point in time had a value of 5, then the sampler would be x of n would be 5. The quantizer would say, you know what, I don't have the right number of bins for that, so we're going to round that to 4. And then this becomes 1, 0, 0. And then maybe insert some check bits or whatever else you want to do. And so that's how, this is the story of how a signal becomes a sequence of bits. And you probably all knew that already. But the other way is mildly interesting if you want to talk about that. So then the source decoder and then ... this is the channel coding, etc. So we need to take a sequence of bits and put them through the opposite of a discrete encoder, which would be a discrete decoder. So that would be check the bit sequence for any errors and use your forward error correction to correct for those. And then those we then pass through a table lookup. So this would be something like every 3 bits that come in, map that to a value. And then we'd have to put this into a digital to analog filter. And then out the other side is another continuous time waveform. And I just love the meta nature of this, is the fact that I'm doing this, or not me, but we are using technology that is doing this right now, right? The pressure wave coming out of my throat is ending up in your ears as another pressure wave, but all of this is happening in real time as I'm speaking, literally. So I just, yeah, no duh, but it is kind of cool to think about. We get to be all meta about this because we're communicating digitally. All right. Just let me have my small victories here, all right? So let's break down the channel encoder. Unless there were questions on that slide, which I just summarily dismissed. Okay, so let's explode the channel encoder. So we just said that these are bits coming in. And the very first thing you want to do is change those bits actually back into signals. So when I talk about signals, I actually mean, so this is the choice. This is when we have to get into the new terminology. So this is going to be bits to symbols. So in communication systems, a symbol is a way to aggregate multiple bits into a single unit. Now, the very simplest aggregation is 1 bit becomes a 1 symbol and a 0 bit becomes a 0 symbol. All right, so there is nothing to be done here if you want to do the simplest encoding there. But another example of a bit to a symbol operation would be quadrature amplitude modulation, so QAM. So for example, if we look at the real axis and the imaginary axis, you can imagine 4 equally spaced points in the 4 quadrants. Now, if I change, and so, okay, clearly there are 4 points here, 4 symbols, which I'll eventually call them. And in this particular lookup, they are just complex numbers. So each of these is a symbol. In fact, it's kind of r e to the minus j pi over 4. So thinking about symbols as complex numbers is a useful shorthand, but you don't have to. Now there are 4 symbols here, which means that each symbol can encode 2 bits. So you can think about this being the 0, 0 symbol, this being the 0, 1 symbol, the 1, 0 symbol, and the 1, 1 symbol. So this is what I mean, mapping bits to symbols. So depending on the bits that come in, we are going to output a different symbol. And if you want to think about symbols as complex numbers, I think that's a smart way to do it. Now, you will also see this operation with different axes labels. So I plotted them with real and imaginary. You will also see this plot with I and Q. Okay, and it's endlessly frustrating to me that they put the in phase on the real instead of the imaginary, because now I is horizontal instead of vertical, and I'm going to screw that up. But these stand for the in phase, or if you like, the cosine part, and the quadrature, or if you like, the sine part. Okay. And thinking about it in terms of an IQ diagram, not intelligence, but in phase and quadrature, is helpful because it maps these complex numbers back to real waveforms immediately, right? So this symbol has this much cosine and this much sine, if you were to think about it as a continuous time waveform. Okay. And so this, sorry, I didn't label this. This is an example called Quadrature Amplitude Modulation. And it is one of a number of ways that we are going to map bits to symbols, and then symbols then get mapped to waveforms. So then we do the next operation. So symbols to waveforms. And for QAM, this is actually we just talked about it. Is this symbol would end up being so we can run this example through. This would be kind of R cosine omega baseband t plus pi on 4 plus R sine omega baseband t plus pi on 4. Okay, so I picked QAM because it's kind of the most obvious of, if I have a symbol in the first quadrant here, then that is a positive amount of cosine and it's a positive amount of sine. And those phases are wrong, I'm sorry. These are pure sines and cosines. That's actually one of the benefits. Plus R sine, okay. And this is why it's called quadrature amplitude modulation, even though it looks like we're changing the phase, is because a 0, 0 bit, we said, maps to this, but a 0, 1 bit would map to what? Negative R cosine omega bt plus R sine omega bt, because this is a negative on the in-phase axis and a positive on the quadrature axis. So that becomes a negative on the in-phase component and a positive on the quadrature component. Questions on that? So this basically is abstracting both of these together. But in principle, you can think about an intermediate, what's called a constellation diagram. Constellation diagram that shows where on the complex plane your symbols all live.
Quick question. What if you want more points on the QAM diagram? Would you just add more bits?
Yeah, you couldn't call it QAM anymore, but you could. Okay. So there is, things like 16 QAM, 64 QAM, and what each of those well, the 16 quam. I won't do 64, but it's 4 symbols in each quadrant.
Okay.
Yeah, so now I can handle 4 bits at a time. Every symbol contains 4 bits worth of information. And the price I pay for that is a couple fold. So I now have to talk about multiple different amplitudes in both directions. That's not terribly hard to do. We can split amplitudes, we can double amplitudes. That's not so bad. But I want to see if you follow this line of reasoning. That if we send, say, this constellation point, this symbol, on the receive side, the received information is going to be noisy. But if we pass that noisy waveform through a decoder, whose job it is to take a continuous time thing and map it to one of these symbols, can you see how having a denser constellation is more error prone for the same noise magnitude?
Yeah.
Yeah, up in this picture, if I were to miss by that amount, then my decoder would still say, oh, look, it should have been that symbol. Success. If I miss by the same amount over here, now all of a sudden I get decoded to that symbol and I screw up some bits. Okay, so that's a very loose argument for why increasing the number of bits per symbol can increase your data rate, right? If you send the same symbol rate, you get more bits per symbol, but in the presence of strong noise, you make more errors. So did you really come out ahead? That's the question. That's actually, that's the question of this class, if you wanted to put it in one sentence.
In the constellation diagram with the 16,
Mhm.
is the first quadrant all still 0, 0, or does each x get a different value now?
Each symbol would take 4 bits. So however you wanted to line this up, that would be quadruple 0, 1, like so, right? I could count from 0 to 15 because I have 16 x's here. So I could map a sequence of 4 bits to every symbol.
Mm-hmm.
Yeah, if you chose to map all of them in each quadrant back to 2 bits, then I don't think you'd be coming out any further ahead than if you just did regular quam, 4 quam. Those are great questions. Anyone else? Okay. Okay, so lastly, we have this kind of baseband, and I've tried to communicate this to you that we're talking about kind of low or intermediate frequencies here. Then we modulate up to the passband. Now, so each of these, with the exception of the middle one, they all can be the null system. They can be the system that does nothing, right? We talked about how at its very most basic form, 1 bit can map to 1 symbol and a 0 bit can map to a 0 symbol, and you've done your bit to symbol mapping. Those then have to become waveforms, so we can't skip the middle block. But again, if you're doing wireline communications, this is optional. Sometimes you can just communicate your data in the baseband and there is no need to upmix it. So this is required for wireless. And I'm going to use wireless and RF kind of interchangeably, even though nowadays wireless is exceeding RF. Call me old school, I guess. So it's optional if you're doing wireline, but it's required if you're going to do wireless.
Question: what are raised cosine filters used for?
Sorry, Ricardo, one more time.
What are raised cosine filters used for?
So raised cosine filters are used to take these kinds of waveforms. So we've already mapped our symbols into voltage waveforms. And you can think about, if you choose something other than sines and cosines to represent these, then, for example, if you think about this not in terms of sines and cosines, but in terms of return to zero or non-return to zero, that kind of business, the presence of sharp changes in this kind of waveform can lead to spectral spread. Right? So if I have this that lasts for TB seconds, or TS, we're going to start using for symbol time, then in the frequency domain, this goes on and on and on for lots of different frequencies. And so sometimes you can neglect everything above and below a certain number of 1 over TB. But what a raised cosine filter does is it strikes a compromise. So this is going to be kind of foreshadowing. That it's not news to you that things that are sharp in the time domain require high frequency components in the frequency domain. So what if we had a trade-off? What if we smoothed out this corner in the time domain? Maybe that would allow us to suck in our frequency spectrum in the frequency domain. And so a raised cosine filter is a formal way to talk about this trade-off, because they have a parameter called alpha, which allows you to talk about how much of this corner do you want to cut, literally, in exchange for the sucking in of the power spectral density. So I call that foreshadowing because I do want to talk about it, but maybe not today. But a raised cosine filter would likely live maybe either in the front end of this block or in the tail end of that block.
Thanks.
Sure. Okay, cool. And then I guess I don't have any room, but the channel decoder would be the opposite of all of these, right? It would be undoing everything we've just done. Okay. And I hope it makes sense that this order is the order that one should do these things in. There's no point in upmixing your bits to RF and then doing some kind of symbol manipulation on them. You'd rather do everything in low frequency, kind of slow time that you can, and then at the very end, upmix it. Okay, so let's talk about the different considerations. So this is digital comms considerations. And honestly, this slide could probably fit into every single one of your 400 level classes, because the stuff I'm going to talk about isn't, well, by and large, isn't specific to digital communications. It's basically the trade-offs that we ask every engineer to do on a regular basis. So there's a phrase for what I'm about to talk about, and it plots them all on these kind of spider web diagrams. I don't think that's the true name for it. Radar plots? I don't know. Anyway, let me stop talking about what I'm going to talk about and talk about it. So how much time do you have to do the processing you need to do? So for us, this usually comes down to what is the minimum data rate that's acceptable? Another dimension that you need to consider when you're talking about a digital communication system is how much spectrum do you have access to? Now this can be bandwidth of the channel, is how we usually think about it. But also, technically speaking, it's the bandwidth of all your components as well, right? I can't I can't process things with a wider bandwidth than whose filters I already have. So it could be talking about the bandwidth of the channel, but also potentially bandwidth of the receive and transmit equipment. If I have unlimited time and unlimited spectrum, I still need to consider how much energy I need to budget. So this has two main considerations for us. This is more like, how much battery life are you going to use to transmit each bit? But on the other end, like on the complete other end of the milliwatt to megawatt scale, how much power can your base station radiate without giving people cancer? So on the other end, it's base station safety. Right, because I can't just pump unlimited amounts of RF power and say, oh, look, I have 0 bit errors because I'm transmitting with a gigawatt of RF power. That would work, but people wouldn't appreciate it. In digital communications, we also need to talk about, in addition to like actual bit rate, how frequently do bunches of bits need to be transmitted? So if you want to think about this in terms of data like aggregation. So when I say data aggregation, I mean, are we trying to stream video that needs to come through in the correct order and with minimum time delay? Or are we sampling the temperature at some remote fire lookout? And whether those packets get delayed by a couple of seconds isn't going to affect anyone's lives. So is there, is the variance of the data rate important or not? So. And then, of course, I can't talk about engineering decisions without talking about cost. We, of course, give you your bachelor's degrees and never make you take any kind of finance or anything to do with a dollar sign, as is tradition. But you need to strike a balance with how much all of this is going to cost. And then also unique to digital communications is, what is your allowable error rate? So, and this is what I was talking about with the kind of the spider web diagram. If you can plot how important each of these dimensions are to your project and whether your diagram looks like this or whether it looks like that, will affect which system you're going to implement. Yeah? And honestly, there are probably way more dimensions than we can fit on this graph, but I don't particularly like these spider webs because they connote meaning to adjacent dimensions that shouldn't be there. Like if I were to write these in a different order, the graphs would look totally different. And I think that's a poor feature of these kind of radar diagrams, but that's neither here nor there. So maybe talking a little bit more about error rate is, there are some instances where we can tolerate more errors than in other instances. An example of this is actually video conferencing. If we are only sending video, we can treat the audio for another day. If we're only sending video, then you might not believe this, you can actually have a higher error rate in a video conference than on a phone call, and people will not complain. It's way harder for the human ear to pick up garbled audio than it is for the human eye to sort out laggy or glitchy video. And so depending on which one you're doing, you're going to have different requirements for error rates. All right. I think there's no way to do the next thing that I want to talk about in 9 minutes. So I'm going to bank up, which I've actually probably already exhausted. I'm going to let you go 9 minutes early because I've probably held you over for 9 minutes in the past. Or we can open up for questions. This is a kind of a touchy-feely lecture, but sometimes that's all right. So that's all I wanted to say, but I'm happy to answer your questions if you want to hang out.
Question or was someone you can go. You can go if you want. Mine's not too important.
Sure. So for something like QAM and how there's different bit rates that you can send, is that something that's like you can like actually just like hit a switch and then the system goes from like QAM 4 to QAM 16 based on noise detection? Is that?
That's exactly right. That's actually one of the features of LTE mobile communication is the allowance for, or in the protocol, the allowance for switching modulation schemes based on noise measurements. So your phone, if you bought it in the last 6 years, has a feature where it tries to detect the strength of the noise in the channel. And if that noise crosses a certain threshold, then it will stop modulating at 64 QAM and go down to 16 QAM, which means the data rate gets cut in half, but more of those symbols get successfully decoded.
Does that have to do with the bars at like the top corner?
Yeah, so the bars are, well, if they're anything, they are an indication of signal to noise ratio, right? There's always a possibility that they're just there to make us feel better. But yeah, what those bars represent are not necessarily the power that has been received, but they are the derived SNR of the incoming signal.
That's cool. Thank you.
Mm-hmm.
How does cost correlate, let's say, like mathematically, or at least like if we were doing like a problem, how do we look at cost that way? Or is it more of a correlation to kind of the other 5?
Well, yeah, so the cost is going to be a function of the other 5. It's easiest to think about this in terms of like binary choices. If I have a choice between sampling at 100 megahertz and sampling at 200 megahertz, the cost for those two ADCs is going to be different. And that will have ramifications down the line. If I transmit at a higher power, that's going to suck more of my battery life, but perhaps I don't have to buy as sensitive equipment because I'm only going to be trying to decode quote unquote loud signals. Yeah, so you're right. They're all intrinsically tied to each other. That compromises you make in one will have ramifications in the other, and cost is no different.
That makes sense. Also had another question. I thought I'd ask this now since it's about error detection. How in the source encoder, I didn't think I should ask that since you were going to go into it, but since we have extra time,
sure.
As well. So you said that like when you go to a binary interface, you could have ones become zeros or flipped in some sense. Is that due because of noise?
Let me see if I can go back. So was it on this slide that you're talking about?
Yes. So we're looking at error detection. You said that from the source encoder to the channel encoder, or is it made from the audio to the?
So yeah. So let's say that we have a 0 bit, and that bit gets changed into kind of symbol number 0, whatever that happens to be. That symbol gets changed into waveform number 0, whatever that happens to be. That gets mixed up to kind of the passband version, whatever that happens to be. And then that gets sent through the transmitter, through the channel which will involve, we could model potentially some additive white Gaussian noise, which means that the received signal will not be what was transmitted, but it'll be some different version. We could then mix that from passband down to baseband. And we could then have, and this is what gets to the heart of your question, is that based on what Y0 is, whether that gets decided to be S0 or S1, this is the chance for error.
Okay.
Okay, and so we're going to learn some tools to decide like what features of Y of 0 would lead to error and what would lead to correct detection. But then like this last step is usually not error prone. This is just a lookup table. So the error would almost always come from going from the continuous time waveform to the decoded symbol.
Okay, that makes sense.
Yeah.
Oh, and based on what we looked at, the QAM, if those could be another reason too.
Yeah. So if this is what you transmit,
I mean, if you use that system, right?
If this is what you transmit and this is what you receive, any logic, and this is like people complain that, well, what if we just made a more intelligent decoder? But there's no way to make an intelligent decoder that looks at this receive symbol and doesn't map it to that constellation point.
Okay.
Right? Because the decoder can't know what was sent. All the decoder can see is what it receives. And if you tell me that you're going to tell me a decoder that takes this symbol and maps it to that symbol, that's terrible. Like you've sold me a bad decoder. Yeah.
Okay.
This has to be mapped to this one, and that will lead to errors.
Okay, that's cool. Thank you for that.
You're welcome.
I guess we'll learn more about it soon.
I hope so. That's the hope.
Awesome. Well, thank you. I'm good here. Have a nice day.
Thank you.
Clay, quick question. I know this falls more into the realm of SI, but will we be looking at characteristics of eye diagrams and how to improve, like, what do you call it? The opening, because that's basically data rate transitions.
Yeah, actually, that's one of the things that I'm going to include this quarter that I haven't included in this class in previous quarters is interpretation of eye diagrams. So I'm hoping that I can get some kind of simulation, or perfect world, I would set up a little mini hardware setup and show you how to set up an eye diagram and all that stuff. But at the very least, we're going to talk about the features of eye diagrams in either this unit or the next. So it's coming up soon. But if I can get my act together, we might actually have a demo on some hardware.
All right, I'll hold you to it.
Okay.
Clay, quick question.
Go ahead.
If they're asking you to build a receiver, and that receiver is going to have a certain IF power, a certain IF frequency, and the output of this receiver, quote unquote, that you're going to measure the EVM of it, this means that your receiver stops after the passband to baseband conversion, right?
So if you're measuring the EVM, which for those not in the know, that's error vector magnitude, then you actually, I think, you need to go all the way to symbol decision. So going back to the chain of events here.
The EVM is being measured outside of the DUT, which is called the receiver in this case.
Okay. So it sounds like your receiver needs to output symbols, decided symbols. Is that not true?
Well, you can't measure EVM on decided symbols, right? EVM is measured on where your point is in the constellation diagram. And I think that's right after your passband to baseband conversion.
Okay, yeah. So I guess maybe I was using the wrong terminology, but you need to output this point, and then someone else will decide whether that was an error or not, and how big of an error that was.
Yes.
Okay. So yeah, sorry. Going from passband down to baseband, and then yeah, someone else will take that symbol and do the error calculation on it. Was that your question?
Yeah.
I feel like the question turned into me asking what your question was.
No, The thing is, this project defines it doesn't really define where you have to stop your receiver at, but by looking at it, it says that the EVM is going to be measured outside of your DUT.
That's not terribly surprising because to calculate EVM, you need to actually know what was sent. So it would be like having a referee flipping a coin, sending a symbol, but you don't know what was sent. But then you hand that referee what you decide, and then the referee measures the error.
Okay, yeah, that's the part. Like they know what is sent out, and they get the received signal, and they kind of do that thing.
Yeah, that makes sense.
Okay, so it's basically just like the front end of a receiver, basically.
Sounds like it, yeah.
Yeah. Okay. Well, I was just kind of like trying to figure that out.
Yeah, I'm glad this fits in with that.
Yeah.
Okay, I told you I'd let you go early, and now it's 2 after. All right.
Thank you.
Goodbye.
Thank you.